all events happen in space and in time. And that's what makes physics so wonderful.
So, Lawrence, away you go.
Okay, from the ridiculous to the sublime. First of all, I forgot before. I wanted to thank Anthony and Miriam and Richard when I asked them to do this. They all have very busy schedules, and I was so pleased that they immediately said yes. And each of them, I mean, it's always a pleasure for me and an honor for me to be able to be on the same stage or whatever with them, because each of them in their own way is so eloquent and powerful about different ideas. And for you, those of you who haven't, every time I hear Miriam speak, I just love it, because I'm go all fired up. And it's incredibly important and brave, much braver than anything I do, so I admire all of them. So thank you all for agreeing to do this and take time out of your busy schedule to join us. I'm going to just spend a few minutes, because I'm going to get to talk later with Richard. I thought I would talk about 3 examples, because science is the prototypical example of humanity's, in principle, ability to change our minds. It's not just an ancillary part of science, it's a central part of science. So I just picked 3 examples of this, and 3 case studies, and hopefully they're about 5 minutes apiece, and then we'll get to there. So let's just see if this works. Okay, I brought my own clicker this time for those of you who are in London. Okay, the first one is the static universe, which was, for eons, for a long time, the conventional wisdom in science was that the universe was static. It's reasonable, because when you look out, the universe is the same day after day after day. And in 1916, Einstein brought us into the modern era with his general theory of relativity. I put this down. You all understand this, so I probably don't have to. But it changed the world. It changed our understanding of gravity. That was 1916. But it didn't change our understanding of the universe at that point, and even for a long time afterwards. In 1925, this is a picture. I always ask, this is not our own galaxy. And I always ask people why. Just to see if you're still awake. Okay. Yeah, we live in our own, most of us live in our own galaxy. And this is the Andromeda Galaxy. But by 1925, actually, was about the time when Edwin Hubble first discovered the existence of other galaxies. But still, if you looked out at the other galaxies, our own galaxy, it's static. And the conventional wisdom was in 1925, less than 100 years ago, that the universe was static. And that was what was, and Einstein was convinced of that, and so convinced that he worked on trying to understand how his theory of general relativity, which should be a theory of the universe, could describe a static universe. And he worked a long time to try and do that. Interestingly enough, however, in 1927, here's Einstein with Belgian priest, Georges Lemaitre, who also is a physicist, and an astronomer as well. They met, and Georges Lemaitre had actually solved Einstein's equations. So Einstein didn't, but Georges Lemaitre solved Einstein's equations for a universe that looked like the universe we live in, okay, with matter distributed as we would in our universe, and argued and demonstrated that it didn't allow a static universe. It required a universe, as he argued, that would expand. In 1926, he published a paper which was later translated. It wasn't originally in English, he eventually called it the primeval atom. He showed that that general relativity required an expansion of the universe and meant, therefore, that our universe had a finite lifetime. Now, Einstein's response in 1927 was, your calculations are correct, but your physics is atrocious. Okay? But the great thing was that Einstein was ultimately influenced by data. This is 1929, Hubble's first measurement of the velocity of galaxies away from us as a function of their distance. And as often discussed, drawing a straight line through this data set is not rational at all, but anyway, he did it. And arguing that, in fact, more distant galaxies were moving away from us more quickly than closer galaxies. The first demonstration that the universe was, in fact, expanding. That was in 1929. Within 2 years, when Einstein again met Lemaitre at California Institute of Technology, he had changed his picture a lot. As he said, this is the most beautiful and satisfactory explanation of creation to which I have ever listened. Okay, in 4 years, changed his mind completely from something he was definitive about and rather offensive in his words to Lemaitre, and changed it so much that in fact he wrote a preface for Lemaitre's book, The Primeval Atom, and helped translate Lemaitre's paper into English so it could be published for the rest of the world to see. The idea being that this conviction that we lived in a static universe, which had driven Einstein for all of the period between 1916 and 1926, was changed in a moment by good theory supported by good evidence. It's interesting, by the way, that Edwin Hubble never accepted the expanding universe, in fact, in spite of the fact that he proved it. But that's another example of a very important law of science, which is, as Max Planck once said, physics proceeds one funeral at a time. But so this is the first example of my bunch, that we're willing to change our entire picture of the universe for a little bit of evidence. What a remarkable thing. Next one. This is a little self-serving, but I'll be self-serving in this case. Dark matter and dark energy. I lived through this era. And as my entire career as a scientist, in some sense, spans this era. And so what's omega? Omega is this quantity. Einstein's general relativity told us that space can be curved. And so once you know space can be curved, the question is it curved? And it turns out a three-dimensional space can be so-called closed, like a three-dimensional version of a sphere, or so-called flat, which is not like a pancake, but a flat universe is one in which the x direction always heads in the same direction. It's perpendicular to the y direction, which is perpendicular to the z direction, and they always point in the same direction. It's the universe you think you live in, a flat universe, or an open universe. And it turns out that depends, because Einstein said the geometry of space is determined by the amount of matter in the universe. So therefore, if you could determine the amount of matter and energy in the universe, you would determine the geometry of the universe. And omega was just a Greek letter that represents whether the universe is open, closed, or flat. If it's much less than 1, the universe is open or negatively curved. If it's greater than 1, the universe is closed, like a closed sphere. It closes in upon itself. Space will turn back in on itself. And if it's flat, it's just this universe we thought we lived in. And all of the data, we add up the amount of matter in the universe by counting galaxies and counting the number of stars in galaxies, and we know the mass of the sun, and just doing an accounting of what we can see in the universe had definitively established by 1972 or so that the total amount of matter in the universe was roughly 1 to 2% at most of what was required to produce a flat universe. So the conventional wisdom was, at the time, that the universe is open. In the 1970s, Vera Rubin, who's passed away, but was a friend of mine and an amazing astronomer, showed that, in fact, well, there's a significant undercounting here. It's quite simple. When you look out at the night sky, you see the things that shine, but you don't see the things that don't shine. And she showed, by a very interesting methodology, and other people as well, she wasn't the only one, that in fact there's much more matter in our galaxy than you can see, which is not surprising. You know, the universe is filled with snowballs, theologians, whatever, they don't shine. And so she demonstrated by using Newton's laws that, in fact, there was much more matter in our galaxy than you could account for here. In fact, almost perhaps 10 times as much matter in our galaxy as you could account for adding up all the stars and hot gas and everything that shined. Okay? Well, that's interesting. Then, in a seminal theoretical paper, Alan Guth demonstrated that you could kind of only understand the early history of our universe, most likely, if there was this period called inflation that I'm not going to go into. But one of the predictions of inflation in general, although it turned out it was malleable, was that we live in an exactly flat universe today. The history of the universe would only make sense if the universe was exactly flat. That was very powerful and convinced theorists like myself that was the only sensible universe. Observers were a little more picky because they said there's no evidence of it. But the things began to change because, look, there's at least 10% of the density of the universe and much more than we see. And surely if there might be enough dark matter to account for everything. And in fact, what we discovered, lo and behold, was when we looked at dark matter in other galaxies in the 1980s and measured the mass of clusters of galaxies and larger systems, lo and behold, the amount of dark matter increased. And now omega was at least 0.2. So all evidence suggested, and certainly by 1990, the conventional wisdom was that there must be enough dark matter to make the universe flat, because it's certainly getting larger and larger. But cracks begin to show. And in 1995, we showed that a flat universe requires something crazy. And I'm going to show, I think I'm going to show a picture here that from our 1995 paper, which really doesn't matter. I mean, the details. But we said, look at all the observations of cosmology. And this is omega matter. This is a flat universe here. And this is the Hubble expansion rate, the rate of the expansion of the universe. Measurements had showed that this quantity h had to be above this dashed line. And we said, look at something called Big Bang nucleosynthesis, the way the abundance of elements was determined in the early universe. Look at the age of the universe, which was this. This was a very serious concern. The age of the universe appeared to be too old to account for a closed universe. You notice that the universe would get younger and younger the more and more matter you had in it. And evidence was that our galaxies appeared to be older than the universe because we knew our galaxy was at least 12 billion years old. And if you had, it turns out, if you had a flat universe full of matter and the Hubble constant was as large as it was, then the universe would be less than 10 billion years old. And it's embarrassing when the galaxy is older than the universe, okay? And then there were other things. There was a clustering of matter in the universe. There's a cosmic microwave background. This was a lower bound. The lower bound I told you about basically now had been moved up to 0.3. Omega matter was up here. And what we argued was that all the data was inconsistent with a flat universe with omega equal 1 and a Hubble constant equal or greater than the value had been here. In fact, the data was only consistent in this small region with a flat universe if omega matter was about 0.3 or between 0.3 and 0.4, and that meant something else had to have the energy that would be necessary to make the universe flat. Now, when we proposed this, I didn't believe that the only way you could get all the other energy, if you'd added up all the matter, was to have put energy in nothing, if empty space had energy. And this is an absolutely insane idea. It's one that Einstein came up with, but he discarded. But it's ridiculous. It's patently ridiculous. And part of the intent of that paper was to show that you were driven to absurdity, and therefore some of the data must be wrong. Okay? That was at least what I thought. I thought, look, you're driven to a contradiction. Something must fundamentally be wrong with the data. Okay? And I lectured on this around the country. People smiled and ignored it because it is ridiculous. I think we said we're currently facing a crisis. This was the last paragraph. A crisis in cosmology that is once again driving us to consider the possibility that the cosmological constant, that's the energy of empty space, is non-zero and dominates the energy density universe. The challenge this poses for fundamental physics is dramatic. If in this third event to invoke a cosmological constant, cosmologists are finally correct, the impact for understanding of both the universe and fundamental physics will be profound. Well, it was necessary to write that, but I didn't believe it, okay? Because I just knew it was ridiculous, okay? Because if you have energy in empty space, this equation of Einstein changes, and you have to have, and you add an extra term, and that's the energy of empty space. Why should empty space have energy? There's nothing there. But it appeared to be required that 70% of the energy in the universe resided in empty space if you want to make it consistent. And I have to say that in 1995, this notion was absurd because it violated our picture of what was sensible in the universe. In 1998, observers, and again, this is a complicated picture, measured the expansion rate of the universe. And the interesting thing is, if you put energy in empty space, it's gravitationally repulsive. It's not gravitationally attractive. And that would cause the expansion of the universe to speed up. And these observers have been trying to measure the rate at which the universe is slowing down, because gravity sucks, okay? And they tried to measure it by looking at distant objects, supernovae, across the universe. And to make this picture more understandable, draw a straight line through it and bring it horizontally. And what was expected was that the universe would be slowing down over time, which would be this dashed line. Instead, what the observers discovered in 1998 and 1999, to their shock and initial dismay, they later got very happy about it, it was very good to them, is that the universe was not slowing down, it was speeding up. And if you tried to fit the data, what would be the best fit? The best fit to the data was 30% of the energy of the universe was in matter and 70% was in empty space. Within 1 year, that was universally accepted. That insane reality, which we still don't understand, the biggest mystery in science is why should empty space have energy, is now the standard model of cosmology. And the observers who made this discovery within 10 years won the Nobel Prize for discovering, well, as I like to say, for confirming our prediction. But for discovering something, and it's perfectly reasonable because no one believed the prediction, but everyone believed the observations. Because it wasn't the only set of observations. It turned out that ultimately it was confirmed by other things as well. Because the data matters. Because what's sensible doesn't matter in science. It's what nature tells us. That's what we have to accept. If it doesn't make sense to us, it doesn't matter. What we like is not important. And that's the lesson from that. The final lesson of the three is, I think, important when it relates to religion, and I want to put it, because scientific truth, it's probably the least understood aspect, and I have to say many scientists don't understand this either, non-physicists at least. It's what the great successes, almost all, many of them done in England, the triumph of electromagnetism of James Clerk Maxwell and Michael Faraday producing a theory that explained essentially everything we can see, everything that governs everything that's happening in this room. Gravity is irrelevant for the most part. The beautiful, beautiful theory, a triumph of physics. The most beautiful theory in physics, perhaps, electromagnetism. The understanding of Newton of gravity, which changed the world, ended the burning of witches, happily, people think, at least in Europe, by suggesting that bad effects probably had physical causes, not witches. If you could understand the motion of the planets around, if gravity was a single force that explained the dropping apples in an orchard in England, and also the orbits of Jupiter and the Earth and everything else around the sun, if a single theory could describe all of that, then surely we would be able to understand nature as being causal and physical effects having physical causes. And this is scientific truth. But what I want to point out to you is now we know there is no such thing as scientific truth in an absolute sense. And I think it's the biggest revolution because it really hits at the heart of what scientists really wanted to know about the universe. And I want to give you a brief 2-minute example before I end. And that's this theory, the quantum theory of electromagnetism, which tells you how electrons relate with light. This is a Feynman diagram. It's the best theory we have in nature. It's the best tested theory in nature. If we measure something called the magnetic moment of the electron, we calculate it in theory. And here's the experimental measurement of, let's see, that's the theoretical prediction. This is the experimental measurement. there's nowhere else in nature, from fundamental principles, we predict a quantity to 13 decimal places that agrees with experiment. There's nowhere else in science where this can be done. There's no better theory in nature where fundamental principles of the interaction of particles, of electrons with photons, can give you a prediction and that it can be tested against experiment, which is done with unbelievable precision. There's no better claim to scientific truth than quantum electrodynamics, but it's not true. We know it's not true in a fundamental sense because it doesn't describe nature on all scales. We know that, and in fact, the seeds of that lie in the theory itself. The theory predicts that, in fact, in addition to the particles that make up an atom, protons and electrons, there are these virtual particles popping in and out of existence all the time, on a time scale so short that we can't see them. But those virtual particles have an effect. If we try and measure the charge on an electron, which is something fundamental, it should be fundamental, it depends on how you measure it. Because there are virtual particles popping in and out, particle-antiparticle pairs popping in and out of existence. And if an electron-positron pair pops into space, the positron will want to hang out closer to the electron because it's attracted to it. And the negative charge will be pushed away from it. If we measure the charge on the electron on this scale, now we'll be measuring the fundamental charge plus the effect of all these positive charges. The charge on an electron will depend on the scale at which you measure it. The theory, which has something called the fine structure constant, is not absolute. It depends on the scale you measure it. In fact, if we look at it, we now know that actually all the forces in nature change in strength. And depending upon the energy scale you have or the distance scale you measure them, and maybe up here, maybe up there, they come together to be a new theory. There's no theory of science that we have in physics that is true on all scales. There is no fundamental scientific truth. All scientific theories are provisional. They explain perfectly the phenomena with which they're designed to explain. Newton's law of gravity explains cannonballs and rocket ships around Earth perfectly. You don't need Einstein. It's true today as it was back then. Electromagnetism works to allow us to create the technology on which everything we're doing today is based. But it's provisional. On that scale, it works. On a much smaller scale, electromagnetism doesn't even exist as a theory. It's unified with another theory called the weak interaction, and it looks very different. So we now have come to realize, kicking and screaming, that we who are searching for scientific truth, there is no absolute scientific truth. At least no known scientific theory applies on all scales. String theorists think they may have discovered a theory that does, but there's no evidence of that. And as Anthony described so beautifully, right now, we should be skeptical. So we must never stop being prepared to change our minds. I guess that's what I wanted to show you. Science, by an example, demonstrates that even when it comes to the most fundamental things we think about, a static universe, the nature of nothing, and the nature of truth, the things that many philosophers might say are immutable at some scale, that scientists have been willing to throw out those ideas like yesterday's newspaper when the universe tells us otherwise. And that is a paradigm. That's why science is such a useful example, I think, for the rest of the world, especially compared to religion, which is based on absolute truths, which of course aren't true. Thanks.
Thank you, Lawrence. Are your minds blown, or is it just me?